Hello students, this is lecture 4 of MTH 201. In the last lecture we looked at orthogonal projection of a vector onto another, triangle inequality, cross product of vectors. We looked at the definition and using the concept of triple product we gave a geometrical interpretation for cross product of two vectors. So today we are going to continue our discussion on cross products and also look at a few applications. So let us first look at the length of cross product. Okay, so this is very standard computation. So using the definition of cross product of vectors v and w which have these components, we know that V cross W, we know the definition of V cross W, right, from the last class. So what we have just taken is taken the norm of that and square of that, which comes out to be this quantity. Okay. And if you expand this quantity, you can, after some manipulations, you can write it in this form. Okay, so I'll not go into how to go from here to here. You can just take all the squares and verify that this is equal to this. But now this is something that we know. So if you look at the first term, v1 square plus v2 square plus v3 square, that's nothing but the square of the norm of v. And the second term is the square of the norm of w minus this final term is v dot w square, right? But we know that v dot w is equal to norm v norm w cosine theta, but you have a square, so you get square here. If you take norm v square norm w square common in both the terms, you get 1 minus cosine square theta in the bracket, which is equal to sine square theta. So length of v cross w square is nothing but norm of v square norm of w square sine square theta, where theta is the angle between the two vectors, right? And theta lies in the interval 0 and pi. Therefore, if you take square roots on both sides, you get norm of v cross w is equal to norm v norm w sine theta. So remember, here I have taken sine theta and not absolute sine theta because whenever theta lies between 0 and pi, sine theta takes positive values. So therefore there is no problem, right? Because length of a vector has to be a non-negative number, right? It can't be negative. But there is no problem here because sine theta is positive and anyway you know that norm of v and norm of w are also positive. So this is the definition of, this is the length of the cross product. Okay. Now let us understand the length of cross product geometrically. So I want you to look at this parallelogram that is shown in the picture, whose adjacent sides are A and B, and then you complete the parallelogram. So what is the area of this parallelogram? Okay. So if you, so what is the area of the parallelogram? It's length of base times height, right? So I'm considering base to be this. So what is the length of the base? It's norm A. And what is this height? So height can be computed using right angle triangle formula. This angle is theta. So if you look at this triangle, the hypotenuse is norm B, which is the length of this vector B. So this height comes out to be norm B sine theta, right? So then what is the area? Area is norm B sine theta times norm A, which is the base, which is nothing but norm of A cross B, right? Which we saw in the previous slide. Now in the above figure, there are two vectors n1 and n2, which is n2 is equal to minus n1, which are both perpendicular to A and B. Remember, A cross B geometrically meant, what did it mean by triple product? That any vector that is perpendicular to any vector that is spanned by A and B, right? In particular, A cross B is perpendicular to A and A cross B is perpendicular to B, right? So this is what you get, right? Now, using the right hand rule which we saw last time, N1 is equal to A cross B. So you curl your fingers from A to B, and wherever your thumb points, that's the direction of A cross B. So in this case, N1 comes out to be A cross B. So we say that a parallelogram spanned by two vectors A and B if the vectors A and B are two adjacent sides of the parallelogram. So this parallelogram that you see in the picture is a parallelogram which is spanned by vectors A and B because A and B are adjacent sides of this parallelogram. And we just noticed that area of this parallelogram is norm A, norm B sine theta, where norm A is the length of the base and norm B sine theta is the length of the height, and this equals norm of A cross B, which we saw in the previous slide. So what does the length of cross product signify? It is nothing but the area of the parallelogram which is spanned by the vectors A and B. Hence, the length of the cross product A cross B equals to the area of the parallelogram which is spanned by the vectors A and B. Okay. Now, what about the direction of cross product? This we saw last time. You take your right hand, you start curling your fingers from vector A to vector B, and wherever your thumb points, that's the direction of A cross B. Okay, so that's what is shown here. Now, let us understand the geometrical significance of, so what is volume of parallelepiped? Okay, so what is a parallelepiped? It is basically an extension of a parallelogram in 3 dimensions. Okay, so if you look at this parallelepiped, this face of this parallelepiped is spanned by vectors A and B, and the third direction is spanned by, is given by the vector C, right? So now with these 3 vectors, you can completely describe a parallelepiped, right? You just extend the direction so that you form a parallelepiped. So let us understand what is the volume of this parallelepiped. So volume of this parallelepiped is area of a base times height, right? So if you look at this parallelogram here, you know its area, right? We saw it in the previous slide. So what is the area of the parallelogram which is spanned by vectors A and B? It's nothing but norm of A cross B. And what is this height? Okay. So what do you do with the height? You look at this vector C and you look at this vector A cross B. Okay, A cross B is what? A cross B is a vector that is perpendicular to A cross B, right? Now you look at this angle between C and A cross B. Okay, and this angle will give you this height. So let us see how. So the volume of the parallelepiped whose adjacent sides are vectors A, B, C equals the product of area of parallelogram spanned by A cross B, which equals norm of A cross B, and the height of the parallelepiped, which is norm of C sine psi. Why? Because if you look at this height, this is norm C, right? And then this angle is psi, right? So this angle is psi. So if you drop a perpendicular, so if you look at this right angle triangle, this comes out to be psi. So you get norm C sine psi, right? So whatever is this angle psi between A cross B and C, that's the angle between C, right, and this. Okay. So if you take the product, what you get is norm A cross B times norm C sine psi. Hence the volume of parallelepiped whose adjacent sides are vectors A, B, C equals norm A cross B, norm C sine psi, which is I have made a slight mistake here. So in dot product you get cosine psi, right? So you should get cosine psi here, and this is what you will get here. So if you look at the angle, this is psi, this will be psi, and this will be 90 minus psi, right? So this height comes out to be so if this angle is 90 minus psi, this height comes out to be norm C cosine psi, right? Norm C sine of 90 minus psi, which is norm C cosine psi. So I will correct it. So the upshot here is that the volume of parallelepiped whose adjacent sides are A, B, C actually equals the triple product of these vectors. Okay. So now let us move on to a few applications. So the application is going to be the equation of a plane in R3. So but before that, let us look at equation of a line in R3. So what is a line in R3? A line in the space R3 is the set of all terminal points of vectors starting from a given point P and parallel to a fixed vector D. And this vector D is called the direction vector. So if you look at this picture, you consider a point P, okay, and you consider the direction D. Now you draw all the possible vectors in this direction starting from the point P, and you look at where these vectors end, okay, and you collect all such points. So if you are and you just don't consider vectors in the direction of D but also in the negative direction of D. So basically you are taking all scalar multiples of D, positive and negative both, and you consider all the possible points. So you can see that if T is 0, then you are at the point P. If T is positive, you are on this side of P, and if T is negative, you are on this side of P, right? So you consider all the points which are tails of vectors which start at P and are in the direction of D, okay, or are scalar multiples of D. So thus a line is completely determined by a point P on it and a vector D which is parallel to it. So that gives you a line. Now let us understand equation of a line. So there are two forms that we will study. First is called parametric equation of a line in point direction form, where you see a point and you see a direction. Okay. So this is the picture that you saw in the previous slide. So let us call this point P as x0, y0, z0. It's a point in R3. So let these be the coordinates of this point. So this will be a point on the line, and let the direction be A, B, C. So these are the components of this direction A and B. So this is any vector which is parallel to the line. And suppose R is a general point on the line whose coordinates are x, y, z. So our aim is to find this x, y, z in terms of x0, y0, z0 and a, b, c. What is given to us? We are given a point P and a direction D. We want to find the coordinates of R in terms of these. So if you look at this picture, this vector PR is parallel to this vector D, right? So what is this vector PR? PR is given by x minus x naught, y minus y naught, z minus z naught, and it is parallel to the vector D, right? So if it is parallel to the vector D, then there is some scalar t such that this vector is equal to t times d. That's what we mean by parallel vectors. Therefore, if you equate the components, x minus x naught is equal to t times a, y minus y naught is equal to t times b, and z minus z naught is equal to t times c, which is what I have written here. So, what is the point direction form of the line? Now you bring x naught, y naught, z naught on the right hand side. You get x is equal to x naught plus ta, y is equal to y naught plus tb, and z is equal to z naught plus tc, where t varies over r. So as t goes from minus infinity to plus infinity, you get all the points on this line. Okay. In particular, when t is equal to 0, you are at the point P. Okay. So this is the equation that you have to remember. Now, there is an alternate version of parametric equation of a line which is called point-point form. So now you are not given a direction, you are given 2 points on a line. So in R3, if you are given 2 points on a line, there is a unique line that passes through those 2 points. Okay. So suppose those 2 points are P and Q. The coordinates of P are x1, y1, z1, and coordinates of Q are x2, y2, z2. But once you have 2 points, you can compute the direction, right? So if you look at the vector PQ, which is x2 minus x1, y2 minus y1, z2 minus z1, that lies on the line. So therefore, if you take D to be this vector, now this is a fixed vector, right? Because P and Q are given to you. This gives a direction vector of the line, right? Now you have a direction for the line. Now you can do what you do previously. You have D, right? So if you take a general point on the line and you compute PR, PR is parallel to PQ, which is the direction. Therefore, there exists a scalar t such that PR is equal to t times d. Therefore, x minus x1 is t times the first coordinate of PR and so on. Therefore, the parametric equation of the line in point-point form is given by, now in this equation you bring x1 to the right, y1 to the right and z1 to the right, and this is what you get. And as t goes from minus infinity to infinity, you get the entire line. In particular, when t is equal to 0, x is equal to x1, y is equal to y1 and z equal to z1, and you get the point P. Okay. Can you see at when, for what value of t will you get the point Q? Remember, Q is x2, y2, z2. So what is the value of t which gives you x2, y2, z2? It is actually t equal to 1. So if you put t equal to 1, this becomes x1 plus x2 minus 1, which gives you x2. y1 plus y2 minus 1, which gives you y2. And z1 plus z2 minus z1, which gives you z2. So at t equal to 0, you get point P. T equal to 1, you get point Q. Okay. And as t varies between 0 and 1, you get points from between P and Q, this part of this line. Okay. So this is something that we have seen, right? So line segment joining P and Q is a part of the line passing through P and Q, lying between the points P and Q. Now I don't want you to look at the entire line, just look at the portion PQ, right? This portion. So what is the parametric equation of this portion? This is called a line segment, meaning segment of a line. Literally, segment of a line. So this part of this line, what is the equation? Equation is same as before, right? The only difference is now t varies over the interval 0, 1. Right? We just saw that when t is 0, you are at P. When t is 1, you are at Q. And you can see that if t takes values from between 0 and 1, you are between these 2 points. Okay, so this is the equation of a line segment. It's same as point-point form of a line. The only difference is there t varies over all of real numbers. Here t varies only over this interval 0, 1. Okay. So I would like you to take a break right now and then look at the other part of this video. Okay. So let me stop this recording. Let us